atoms, we learned this thing called an energy level diagram. Carbon has 6 electrons in it. 2 of them are in 1s, which would be down here. We don't care about them because those are not valence electrons. Then there's 2 in 2s and 2 in 2p. So we think carbon, when it's by itself, has this arrangement of its electrons. However, when we look at CH4, or CF4, or CL4, or whatever, where carbon is attached to 4 other atoms in a molecule, and we know that it does, when we analyze those 4 bonds, we find that they're all exactly the same. There's not one that's any different from the other 3. Well, that doesn't really reflect on this arrangement of electrons. This arrangement of electrons shows 2 electrons being lower energy than the other 2 electrons, and an orbital being lower in energy than the other 3. How can it be that you have this arrangement of the orbitals, yet all 4 of the bonds are exactly the same? That doesn't seem to be consistent. Well, the reason that it doesn't is because we think that when atoms like carbon try to bond with other atoms, it doesn't leave its orbitals the way that Schrödinger predicted they would be. It actually changes them up. The term that we use is it hybridizes its orbitals. The central atom will hybridize its orbitals to make sure that all the bonds are the same energy. So what it does is it goes from this arrangement with 1 lower than the other 3 and makes all 4 of those valence orbitals the same energy. So this is, when I say free state carbon, that means carbon not bonded to anything. And we expect the carbon, when it's not bonded to anything, to have this arrangement of its electrons. But when it does have to bond to something, it takes these 4 orbitals, 1 and 3, and makes them all the same. And we would call this hybridization, we would call it sp3. And that 3 there means that you've taken 3 p orbitals and hybridized and made the same energy as the s. sp3 hybridized orbital. Hybridization is a fancy word that we use. Like, it means a cross between things. Example I would give you would be a dog. If you have a poodle and your neighbor has a cocker spaniel and they do what they do, then you get a cockapoo, right? Cockapoo is a cross between those. That would be a hybrid. It's got some properties of cockers and some properties of poodles, and so there it is.
Chill out. We're not 5th graders, you guys.
I'm pretty sure.
Pretty sure we are.
We're high school.
We're in high school.
That's why we find it funny, because 5th graders would never do
We might be 17, but we might not be. Eric isn't.
All right. Now, was that okay to change the slide?
Go back. Oh, we got a boy and a girl. I'm not.
Tomorrow? 17? 17? 16? I forget. You guys are sophomores.
We good? Let's go on. Okay. Now, the hybridization goes right along with the coordination number of the central atom. In the case of carbon in the previous slide, carbon had 4 hydrogens attached to it. It had a coordination number of 4. So it needed all 4 of its orbitals to hybridize. In the next case here, we have this carbon. You see how the carbon's coordination number is 3 in this case. That means that only 3 of its orbitals are going to need to hybridize. Well, it has 4 valence orbitals. What happens to the last one? It's going to take its s and 2 of its p's, that's 3 orbitals, hybridize them so they can all bond to the other atoms. But then one of its orbitals did not hybridize. It just stayed as a p orbital. So the ones that hybridize are the ones that are actually bonding to other atoms. And you look at this and say, well, hold on a second. Carbon has 2 bonds holding it to the oxygen. I'll address that in a moment. You remember what the shape of this molecule would be? It's not T-shaped like it almost looks like. It's a trigonal planar. The angle there is 120 degrees. It's the hybridized orbitals that are going to spread apart as far as they can get from each other. Only the hybridized orbitals do. So in the previous slide where we had 4 orbitals hybridizing, that was a tetrahedral shape, whereas this one is just a trigonal planar because we have 3 hybridized.
has not seen this.
Kyle, are we okay?
Well, I haven't seen it around.
Can we do chemistry?
Why is it made like this?
It didn't hybridize. It didn't hybridize.
He's trying to imitate us.
There's a question. What is this P doing just floating like that? And the answer is, that's a P that did not hybridize. These three P's, two of them joined up with the S and all made the same energy orbital. That last P didn't. It just stayed as a normal P. Now, do you remember what a P orbital looks like? It's dumbbell shaped. Right. You remember that? How it comes out from one side of the nucleus and then 180 degrees. You got two double-lobed kind of dumbbell shaped orbital. That P kept its shape. These three hybridized orbitals, they all spread out 120 degrees from one another. And that's what I was addressing up here. One just remained as a normal P orbital. But we're interested in the ones that actually hybridized, and that would be called sp2 hybridized orbitals. Baruch?
Can't you just look at the coordination number?
That's all you have to do. Whatever the coordination number is going to determine what the hybridization is. That means that's how many of the orbitals had to hybridize.
So we don't have to really think about like the...
No, I'm giving you the background on this. You don't really need to figure it out every time.
We wouldn't be expected to explain it.
I don't think so. Yeah. Yeah. The next slide tells the story and is real quick. Spencer? Oh, the next one. Yeah. So what you're asking, isn't that just this coordination number? Yeah. When you have a coordination number 2, that means you need to have 2 of the orbitals hybridized, and that would be considered sp hybridization. 1s and 1 of the p's hybridized, that's 2 orbitals that had to hybridize, that's a coordination number 2. If you need 3 orbitals to hybridize, because your coordination number is 3 on the central atom, that's s and 2 of the p's, so that would be sp2 hybridization. Now when we get to the bigger molecules, when we have a coordination number of 5, the central atom has to have 5 orbitals to hybridize. Well, it's only got 4 valence orbitals. What it does is it borrows one of its d orbitals to hybridize with it. So it would be considered sp3d.
Wow. Just keep on stealing.
Yeah, and then for 6, you need 2 of the d's. It would be sp3d2. And that adds up to 6 orbitals that you'd have all hybridize together.
Oh, split squared.
Now for the next one, Spencer, we'll have to go back, because I want you to see this whole sigma versus pi bond business. You'll remember that. We good writing?
Yes.
Okay, go back to the one before. The non-hybridized P's, remember those are dumbbell shaped, that thing right there. That's where a pi bond comes in. Those are orbitals that can make a bond, but they're not the same bond as the ones that hybridize. These make what we call sigma bonds. That's the Greek letter for S. The pi bonds are the pi is the Greek letter for P, and they're made from the non-hybridized ones. So the hybrid orbitals make sigma bonds, those 3 do. And those are always, sigma bonds are always the first bond that's made between 2 atoms. If you have a double bond, the first one's a sigma bond. You don't ever get pi bonds unless you have double and triple bonds.
You should have a pi day to celebrate pi bonds.
They're worth celebrating. Pizza Pie Day.
Yeah, pizza.
That sounds
I haven't had pizza yet.
Every time we say pizza, everyone just looks at Drew.
Mad at you? I'm never mad at you, Tarun.
I don't know.
For what?
For not getting pizza.
Does that say steak? Oh, steak.
You can't do
Yes, I
pizza
like
on
steak.
mommy. Stop, you have to get it after. No, you should, because then it's gonna eat it all.
All right, we good with that one? Spencer, let's go 2 ahead. I just want you to look at this. We're done at the end of the hour here. Know the difference between these 2 kinds of bonds and the way they look. A sigma bond is this green region right in here. This is where you have this carbon with an unpaired electron and this carbon with an unpaired electron. They overlap. And where they overlap, that's where the 2 electrons are shared. The sigma bond is always an overlap of orbitals. The pi bond, notice these blue orbitals, those are non-hybridized p orbitals. They're just p orbitals, dumbbell shape. this has an unpaired electron and this has an unpaired electron, they can share those. And how can two parallel orbitals share electrons? What they do is they make kind of a bridge across, and the electrons are shared above and below the sigma bond, like that. That's why a sigma bond always has to be made first before a pi bond is made. The book shows pictures of this too. It's worth looking at them and pondering what they look like, because you do have to make sense of your mind. Pi bonds do have two parts. This is not two pi bonds, it's one pi bond with two parts. Because of the p orbital being two parts, you can have electrons shared up here and down here. So the sigma bond is directly between the two atoms. The pi bond is above and below the sigma bond. We will begin tomorrow by looking at some hybridization, and I'll give you a few example exercises, and then we'll go on. That'll be after the reading quiz. Spend the rest of the hour looking at intermolecular attractions. They're important. Thank you, Drew.